So UN has presented the module that deals with the characterization of the site, which is here in the process. Then usually what a user will do is that he will also use the MC module here, which is the machine characterization module. In that module, he will define the machine itself. And if the machine is floating, this is where he will derive and compute the hydrodynamics data. Then the user will have to go to this module, EC, which will compute the energy capture and will help the user to design the array and optimize the performance of the array of devices. Then he will have the opportunity to run the ET module, which deals with the design of the PTO and the control solutions. The module ED can be run to design the electrical and the grid connection solutions, for example, the inter-array cables. And after that, you can run the station keeping module to design the moorings of the device if the device is floating. And in that case, you also have the opportunity to design the anchors. If the device is fixed, then you can have some tools and methodology to compute and design the foundation. And I will try to present you this module. So the station keeping module, which is we will call it the SK module, deals with this part, which is in black here. So for a fixed device on the left, you have the foundation, probably a support structure, for example, a jacket, and you have the device itself, which can be crossing the free surface level or completely submerged. In that case, the station keeping module will deal with the foundation itself, not the support structure. In the case of a floating device, the SK module will deal with the mooring lines and the anchors. In the case of a mooring system, what the station keeping module can do is to deal with catenary mooring lines or taut mooring lines. Regarding the anchors, we can design drag anchors, gravity-based anchors, and piles and suction anchors as well. And regarding foundations of fixed structures, we can have the design of the gravity-based foundation or monopile. What are the main functionalities of the station keeping module? The first one is to assess the mooring system by running an ultimate limit state calculation and computing the corresponding criteria. And we do the same with a fatigue limit state calculation with some criteria as well. What we do is that we have a frequency domain analysis. We don't go into the time domain, we only use frequency domain. And we base the methodology on the DNV-GLOS E301. We then assess the anchors and foundations using also a ULS analysis. We also have the opportunity to automatically design a catenary mooring system in case the user doesn't have one in mind. And this is basically based on maximum offset of the device that is allowable and so that the ULS criteria for the mooring system are satisfied. We also have an algorithm to automatically design anchors and foundations. And the algorithm will find the dimensions of the anchor and foundations so that the ULS criteria are satisfied. Now, if we focus on anchors and foundation, I will quickly go through the ULS criteria that I use for each of the anchor foundation types. For the pile anchor and monopile, we check the lateral capacity, the axial tension capacity, the axial compression capacity, and the steel stress. And we analyze the steel stress and, inside the pile. And those, we will come back to it during the example that I will show you just after with the RM1 example. For the gravity-based foundation, we check the overturning moment, we check the uplift capacity, the bearing capacity, and the sliding resistance. For the drag anchors, we only have this criteria here, which is the ultimate holding capacity, which is usually given by the manufacturer. For the suction anchors, we check the uplift capacity and the lateral capacity, and a general loading capacity, which is the failure envelope. I will now go through the workflow of the station keeping module. So first, the user needs to define the inputs. Some inputs are specific to the station keeping module, so they have to be provided by the user. Some others can come from other modules, like for example, defining the wave and the wind conditions will come from the site characterization module automatically. The user doesn't have to think about it. Well, he has to think about it when he is using site characterization module, of course, but after that, when it's done, then the module communicates automatically. In those inputs, the user will gather the device properties, which mainly comes from the machine characterization module. The mooring system properties have to be provided by the user, as well as the foundation properties. The weather properties, as I mentioned, come generally from the site characterization module. Then the catenary mooring system design is automatically performed if the user doesn't have a mooring system defined. If the user has defined a mooring system, the mooring system is analyzed based on ULS analysis and FLS analysis if required. Then the foundation and anchor design is performed if chosen by the user, and then this foundation or anchors are analyzed by computing the ULS criteria. And finally, outputs are written out of the module and displayed to the user. And in those outputs, we have some design and assessments results. We have the bill of materials. We have kind of the hierarchy, which is used in the reliability analysis in one of the other assessment modules. And we have some environmental impacts results, which also are used in another module, which is the modules that we will present just after this one. We have already talked about this RM1 example, so I will go quickly over that. And I will move to the presentation of the station keeping module interface. When Frédéric has shown us the main module interface, he has presented a tab with all the modules. And when you click on the station keeping modules, you will land on this page here. And you can see on the left side, you have a menu, kind of a tab, and you have a main section inputs with different pages, 5 different pages. You have one page to run the module, and another section with 4 different pages for the outputs. And those 4 outputs are the one that I just mentioned. The first page of the inputs is the device, is used to display the device's position. And this information will automatically come from the EC module. But if the user wants to run the station keeping module alone without running the other modules before, he can also do that. And in that case, he will have access to the field, and he can modify the field here. Here for changing, for example, the position of the device or the water depth at the device position. When this is done, you can move to the second page. And the second page is probably the place where you have most of the work to be done in terms of filling in the inputs. The type of machine will be automatically filled because the machine is defined in the machine characterization module, which is the MC module. So in the RM1 case, it's a fixed device and it's a tidal energy converter. In the wind force model section, you can define if you want to add some wind force model to your device. If yes, then you will have to define what kind of profile you want to use and the exposed horizontal main dimension and the vertical one. And the wind force model will be considered to be a force that is provided by a cylinder exposed to the wind in that case. So in our case here, RM1, we don't the device is completely submerged, so we don't have any wind force. We have a similar thing for the current. In the case of the RM1, we don't want to include any current force here due to a structure. We will include the current force only due to the rotors. You may say, okay, but the RM1 has a pile. Yes, but the pile is part of the foundation. And in the foundation, when designing the pile, we will also consider that a current force will be applied to the part of the pile which is in the water. Moving to the machine characteristics, the first thing you have to input is the mass of the device, but this comes from another module as well, and the thrust coefficient of the rotor of the device. The thrust coefficient also comes from another module, so this will be filled automatically, but you can check that you have actually read what comes from the other module. If you run the station keeping module in standalone mode, you can define your own curve and line by line, or import it from an Excel file. And you see what you have imported in terms of thrust coefficient as a function of the velocity, current velocity. And then if you go further down, you need to input the rotor diameter that you will use. And when you have done that, you need to add the hub position. And in our case, we have 2 hubs, one at 30 meters above the seabed, placed at minus 14 meters on the y direction, and the other one is the same, but it's plus 14 meters on the other on the y direction as well. So you see that here you have 2 rotors of the same rotor diameter and same thrust coefficient curve. Here, this is an option to include during the rotor force computation the orbital velocity due to the wave, so that you consider the currents plus the velocity due to the wave in the calculation. Okay, once you have done that, you move to the last section, which is the foundation section. And here you need to define the soil properties first. The soil properties will typically comes from the site characterization also. And you need to define the soil type, the soil slope. Here, the user need to define a soil safety factor. You can use the default one, or you can specify one if you want. Now go to the load definition. The load definition is the load that will be applied to the foundation for designing it. Either you say that the load will be automatically computed, and in that case, it means that the current will be used to compute the load on the rotors, and this load will be transferred to the foundation, and this is how the design load will be computed. Or you can check manual and you overdrive the system in a way, and you input your own force here, forces and moments. But we will keep it simple and use the automatic computation force. You have a load safety factor here. And here we know that we want a pile, so we select the foundation type selection is not automatic. In that case, it's manual. We know that we want a pile. So we select the pile here, and we don't want to have an automatic design of the pile. We want to check a design that exists. So we click on manual here and we input the different parameters. Among them, we need to choose if the pile tip of the pile is open or closed. So we select open in that case. We select the pile length over the seabed, which in our case is 30 meters. So when the program will compute the total force on the foundation, it will include the force from the rotors due to the thrust coefficient curves, and an additional current force that is applied on the part of the pile which is above the seabed, and in that case 30 meters. Of course, there is also a moment that will be applied on the foundation due to the fact that the pile is 30 meters high above the foundation. The thickness here is the thickness of the wall of the pile, and the external diameter of the pile is 3.5 meters. And finally, you need to input the buried length of your pile here, 15 meters. The last one is the cost of the foundation material, which is estimated to 3.7 euro per kilo here. And then we have defined all the inputs we need. Regarding the device, we can move to the analysis parameters for the ULS criteria. In that case, we can define the different directions we want to test, and we define the 100 years return period for the waves, 8 and 10. In that case, this will not change much because we have not included the orbital velocity to the computation. However, what will change a lot is the value that we input for the current velocity of 10 years. All those values automatically comes from the site characterization module if the user has run it. If not, then you can define it yourself. You then move, you are then finished with all the inputs. You move to the run module section, you see that you have completed all the input pages. You run the module, and I will not take the risk of crashing everything, so I will move directly to the outputs, cheating a bit. The first page of the outputs is the bill of materials. So here you see that the pile foundation that you have described in the inputs, we have only one because we have only one device, and the cost is estimated, the estimated cost is displayed here. The environmental impact displays some results, and I will not go into the details because Emma will talk about that just after me. Regarding the design assessment is a summary of the main type and dimensions of the foundation that are computed. If you have different devices, you can select the results for the different devices here. And the diameter of the, yes, you have the different dimensions of the pile here, and the total mass that is computed. And what is also interesting is the last page regarding the ULS analysis of the foundation of the pile. And here also you can select which device you want to display the results for. And the first table here displayed the ULS criteria for each of the criteria that has been computed for the monopile. So we see that we have the lateral capacity, axial tension capacity, axial compression capacity, and steel stress criterion, which is calculated here and is compared to the requirement, and you get a green passed if it is okay, or a red failed if it is not. And it is interesting also by comparing visually the two, to see how is the margin with regard to each of the criteria. As an additional piece of information, you have the force here that has been used to compute those criteria. So this force is the one that I mentioned just before, and is the sum of the rotor force, or current forces on the rotors, and current force on the monopile. We see that we have a force in the X direction, in the Z direction also because of the weight of the devices and the foundation itself, and moment in Y because of the forces that are applied with a given arm, which is 30 meters in the case of the two rotors. Those information will then be passed to other modules, especially the information regarding the environmental impact here and the hierarchy that are not displayed for the user, but that the user can visualize in some of the modules. I just wanted to show you the case of a floating device. If the device is floating, then you may have to define this one, yes, to define a mooring system. In case of a mooring system, in the device properties, you will have, of course, the device is floating, so you need to define structure hydrodynamics. If you have run the machine characterization module, the hydrodynamics will come automatically here. We cannot display it, but the message will tell you that it has been imported from the machine characterization module. If not, then you can select some default device. So today we have only 2, but we plan to include more. And you can import your own hydrodynamics data, and the format, you can find the format in the help section here. So today we can have a buoy like that, or the RM3 as a rigid body. So it's an approximation, of course, because we have only a rigid body and not two moving pieces. But in the machine characterization module, of course, you can make the computation for two moving bodies. What is also interesting is to show you how you define the mooring system. So you need to define some safety factors, and you can define your own mooring system. So if I go there, I click define my mooring system. So you get a big table, and with three main categories. The first one is to define the line type. The second one is to define the nodes. The nodes are where you will connect your lines. And the last one is to define the lines. In the line type, we have added some default catalogs. So you have some nylon rope and you have some chain R3 quality here. And if you define it from the catalog, you get all the basic data that comes automatically with it. So it's practical. Or you can define one yourself, but in that case, you need to input everything manually. And you can add several if you want. You can add several like that. Same for the nodes. For the nodes, you need to in our case, we will have three mooring lines with a taut system. So that's why I have defined a nylon rope here. Is it the correct one? Yes, it's the correct one. Then I have defined a 3-point, and I select that this point is of type vessel, which means that this point is connected to the device, to the vessel. When specifying the position of this point, we specified the local coordinate of this point in the coordinate system of the device. And we do the same for the 3-point representing the anchors. In that case, they are fixed, so we select fix. And you see that the name has changed here. It's a global coordinate now. So in the Earth fixed coordinate, the anchor points will be for example, this one is as x 350 and set is minus 70, sorry, because the water depth is 70 meters. And you need to check that column for the points where you need an anchor to be added and computed. Finally, you need to define the three lines. So the first one, you select line type 1 that you have defined above. You need to input the length, and you need to select the anchor node and the fair lead node. And the node numbers are those numbers here that you have defined. Since we don't use catenary system here, we use a taut system. We check the option linear spring, meaning that we don't want to model the lines as catenary, but with catenary equations, but with a simple spring equation. We can check that we have defined our mooring system as we want. And we can define the device position as well. Here we put 0 everywhere, so it's at the initial position. We confirm, and if everything works, we get graphical 3D representation of the mooring system that you have defined. What is important is to check that the lines are correctly connected to the points where you think it should be connected. When you have an error in the computation, usually the lines are disconnected from the point they should be connected to. Okay, and you can zoom as well. Oh, of course, everything closed. the live demo effect. I can use the opportunity to show you the documentation. The documentation of the tool of the SK module, which is similar for all the modules. The structure is similar for all the modules, and here in the explanation section, you can have access to different theoretical formulation, like the current force model that we just mentioned is can be seen here, and the rotor force model is, you can check also the formulation here. I'm opening the GUI again to show you the end, but I think that was almost everything I wanted to show you. So I have some downloading happening here. I just closed this by mistake, actually. Okay. Mm-hmm. Okay. I think that was all I wanted to show anyway. Yes, so that was we stopped where yes, we stopped at the mooring system, showing it, and just below the 3G graphical representation of the mooring system, you also have access to the forces that are applied on the device due to the mooring system, and you also have the stiffness metrics that you have due to the mooring system on the device. And you can check that if you move the position of the device, the forces from the mooring system will change, and the stiffness matrix will change as well. Okay, I can try again to show you those two. Open this one, yes. So hopefully we were in the device properties. The mooring system definition, defining it. Okay, check and plot. Water depth is 17. Water density, and check 0, confirm. Okay, then we are back to the plot, and here you see what I was mentioning. You have a table which tells you which force comes from which line. So this can help you to check that the computation were performed correctly. You have the mooring line tension at the 2 points, the 2 connection points. Here they are equal because it's a taut system, so that's okay. And at the end, you have the table representing the mooring stiffness matrix. And of course, if you move the floater, you will have some changes here. So you can use this interface to check that you have defined your mooring system correctly. And then you continue the computation. You run the module, and in the ULS assessment, you will have some information regarding the maximum tension of the line, of each line, compared to the MBL of the line, and if the maximum tension is less, then the ULS criteria will say that it's okay. If it's not, then it will tell you that it's not okay. That's all I wanted to tell you now.